Good afternoon, ma'am.
Yeah, good afternoon. I don't know, I logged my name, but
Yeah, it's fine, ma'am. Ma'am, 12:30 to 1:30 was the lunch time, so the participants are joining. We'll wait for another 5-7 minutes to start the session.
Okay. नहीं होगा. नोएडा.
हैप्पी एनिवर्सरी. क्या बात है. तैयार होके बैठी हो. तैयार होके बैठी हो. भैया का इंतजार करती हूँ.
Dear participant, kindly mute yourself.
अच्छा अच्छा अच्छा. तो लेट आएगी क्या तुम लोग. अच्छा अच्छा. लेट आएगी क्या. मुझे लगा आ गई हो. तो लेट आएगी कि लोग जल्दी नहीं आए आज.
हमारी जानकार रही है सविता अग्रवाल. बातें कर रही है.
हम्म हम्म
Rita ma'am, we are waiting for next 5 minutes and then we will start the session, ma'am.
Bye.
Dear participants, stay with us. We are about to start the session.
Yeah.
Okay. Nice to see you, ma'am.
Yeah, same here.
Okay, we now begin with the afternoon technical sessions. And we'll have a fourth lecture on AI for green chemistry and sustainable industrial processes. I now invite Dr. Ashok Kumar to introduce our esteemed resource person and conduct the session.
ये शेयर कैसे करते
Thank you,
हैं?
Dr. Ashma ma'am.
Yes.
It is my great privilege to introduce Professor Rita Kakkar, an eminent chemist, distinguished academic leader, and former Dean of the Faculty of Science, University of Delhi. With over 4 decades of excellence in teaching, research, and academic leadership, Professor Kakkar has made pioneering contribution to physical chemistry, quantum chemistry, computational chemistry, spectroscopy, and nanoscience. She has authored more than 200 research publications, 8 book chapters, and widely acclaimed textbook published by Cambridge University Press, and has successfully guided over 50 PhD scholars. She currently serves as the Director of Research and Innovation at Siddharth Grish and Loops Private Limited DTU Lab. Her remarkable contribution have been recognized with numerous prestigious honors, including being selected among the 75 women in chemistry by the Royal Society of Chemistry and the principal scientific advisor to the Government of India. Professor Kakkar is an active member of leading scientific societies, has successfully led CSIR funded research projects, presented her books at numerous international conferences, and serves as a reviewer and editorial board member for several high impact scientific journals. Today, Professor Kakkar will deliver an invited lecture on AI for green chemistry and sustainable industrial process. We are honored to have Professor Rita Kakkar with us today. Please join us in extending a warm and heartfelt welcome to our distinguished speaker. Ma'am, we welcome you.
Thank you. I'm trying to share my uh,
Ma'am, there will be a icon share, so you can.
but it is not doing from there. And I mean, after the lockdown, I've hardly ever done online. Because it's not. Zoom
Can you see the share screen?
Yeah,
Share word, share green color.
एक minute.
You just have to press that.
Share. Video. More. There's no share.
There is. Ma'am, in this Zoom platform, you can see the share button, react, participant list, chat, etc.
Chat, react more. There is no
Yeah, there is share.
there is no share button.
No, react, after react, there is a share icon.
There is
More Hello?
Yes,
Yes,
ma'am.
ma'am.
If you send the PPT, we will share it.
Okay, just a minute. Share आया.
Yes. Yes, ma'am.
Yes, ma'am. We can see your screen, ma'am.
Yeah. Let's go open.
You can make it full screen.
Yeah, I'll make it first. Let me go to the first slide. Okay.
Yes, ma'am.
It is
Yes.
visible,
Yes,
no?
ma'am.
So, yeah. Thank you for the nice introduction. Uh, I have I retired from Delhi University 5 years ago, and after that, only recently I've been asked to join Siddharth Greases and Lubes because they have set up a lab at DTU where they want to do innovative research. So I think I'm the right person to talk about how AI is changing the industry now, why industry leaders, the founders, they are looking for AI and computational chemistry. I have, as you said, I have over 40 years of experience doing computational chemistry. And I taught at Delhi University for 40 years. And before I retired, I was the Dean of the Faculty of Science. I was the head of the Department of Chemistry. And since then, even after retirement, I'm active in research. I've published 40 papers in the past 5 years. In this year itself, I've published 4 papers, and these are with my ex-colleagues who are doing experimental work, but then they find it difficult to publish without any theoretical background, because if you are proposing a mechanism, you also have to verify using some kind of calculations. So I've been doing DFT, which students might have heard. Everybody now, it's become a buzzword. I've been doing DFT calculations ever since it was introduced. Before that, we were doing semi-empirical calculations at the lower level, ab initio and all, but DFT has become the workhorse for everybody now. So I have lots of experience in that. And then even, like I said, even after retirement, I'm doing a lot of research. I'm using DFT. I'm also integrating AI into what I do. So that is why I think what I'm saying has relevance to what I'm doing. So, why it is very urgent? Why are we talking about green chemistry and AI? The title itself, I said green chemistry plus AI, how we want to harness it to make our processes green, the industrial processes green. And it is very urgent. Why? Because the global CO2 emissions, 50% of these are due to the industrial chemical processes. Now, almost every industry is a chemical industry. I mean, some kind of chemicals are being made, or so they are contributing 50%. The rest of the 50% is livestock and so on. But this 50% we have to reduce somehow. And about 6.4, what should I say, tera billion tons of is the annual cost of chemical waste and process inefficiency worldwide. So we have to
Yes,
see
now.
that this has to reduce, because you cannot be wasting so much. You know, you already know what is happening due to carbon dioxide emissions. Global warming is there. Even Europe is experiencing temperatures of 40 degrees, which was never there. They never had ACs, but now they are also using ACs. Now here we have the third part is not visible. So I'll just read, because what I'm saying is what AI can do is it is reduced 100 times. Because of this screen, I'm not able to see. So I'll just see from what I'm saying. The third number, it is the most hopeful. AI guided computational screening can accelerate materials and molecule discovery by a factor of 100 or more. So AI plus DFT. Instead of doing experiments just like that mindlessly, you think that some chemical is a better, maybe drug, maybe a better chemical for whatever, and you synthesize it and use a lot of chemicals, lot of solvents and so on, and in the end it doesn't produce any results, and you are just throwing all that into the Yamuna. So that is what we want to stop. We want to use AI, that is artificial intelligence and computational work. In computation also, we are not even synthesizing a molecule. Without doing any synthesis, we are able to predict whether this molecule is going to be effective or not, whether we have to synthesize it or not. So it saves a lot on chemicals, a lot on CO2 emissions, a lot on waste, which is money also. So then we come to what are the toolkits for intelligent chemistry. AI, students probably think AI is only for writing letters, emails, for correcting your language, for helping you do your homework. No, it is much more than that. It is able to do a lot of things, and these are some of the toolkits that it has. The first one is machine learning, ML. That word is also has become familiar, that we all know that from some data, it can AI can generate models which can predict for unknown molecules. So instead of synthesizing first and then getting data for those molecules, you are able to do it without even doing the synthesis. Now, these models, what I've written, QSAR, QSPR, I've been using for years. I think my first paper was 25 years ago when I used QSAR. QSAR stands for Quantitative Structure Activity Relationships, and QSPR model, it stands for Quantitative Structure Property Relationships. You can predict properties, you can predict reaction outcome, the classification of a reaction without doing the reaction. I'm going on emphasizing without doing the reaction, you are able to predict. Now, we had been, I mean, this is nothing to do with AI. We were using QSAR, QSPR long ago. What you do is you take some molecules which have been synthesized, whose properties you know, then see how changing a functional group, changing something changes the properties of that molecule. Why is it important? Because we want to synthesize molecules which do not harm our environment, which our licensing authorities also will pass because they are not harming the environment and which are not harmful to humans. So to do that, we just uh, without manufacturing that molecule, we are able to predict the properties, and that is what QSAR is all about. The second one is DFT plus AI hybrid. Now, this is what I'm talking about. I've spent a lifetime doing DFT calculations, and I'm still doing, and they are still very important because many of my colleagues who are doing experimental research have to publish a paper, they need to show that this mechanism is consistent with DFT calculations. So they all come to me for those calculations, and I've already told you I've published 40 papers after when I should have just stopped doing any research. So that is because they need help for that. And so what DFT plus AI hybrid does is that somebody does DFT calculations. Suppose you want to screen millions of compounds and find out one compound that works as a very good, I'm talking about the industry that I'm going to join, grease industry, which is going to be a better grease. Uh, so you think of lots of molecules with lots of different substituents, different functional groups and all. And you cannot do calculations on all those millions of compounds, but you can do calculations on 8,000 compounds. It will take a lot of time, but still you can do. Getting data from there and feeding it into your AI can help you predict for unknown molecules that you have not done the calculations on, because even DFT takes a lot of time. It takes me days to do a single run. For example, I'm looking for, why grease has become very important. We have Vande Bharat trains which travel so fast that the grease also has to keep up with it. You have to have a grease which will withstand such high speeds. Then other you need in space greases to for lubrication and so on. So this founder, he wanted me just to head that research group, and when he realized that I'm doing DFT calculations, he asked me to help with those, to help AI implement AI in these calculations. So this is one kind of hybridization that we can do. DFT calculation somebody does, That also has its limitations in the sense that it takes time for a single DFT calculation because it is very accurate and you need very good computers for that. And then AI, you do on it and you see the potential energy surfaces, what kind of reaction is taking place and so on. And you do for a series of molecules, and then you can predict for, use that data, feed it into your AI model, and that AI model will do it for unknown molecules for which now you don't have to do the calculation. The third one is that I'm talking about, I'm not able to see what is there. So I was talking about the hybrid. The fourth one is, so now you don't have to do so many calculations. The next one is the generative AI. That is something which is new. Instead of testing molecules, what you do is you describe, one way, the traditional way was that you keep on synthesizing molecules, get their properties, and then decide which molecule you want to work with. But so now what you do is you go to AI and say, I want a molecule which has these properties, and it will tell you what kind of substituent to add. So, wow, मैं नीचे कर देती हूँ. हाँ, I don't want to, है ना? So anyway, what generative AI is something new. De novo now I can read it, I've pushed it up. De novo molecular design, inverse design for target green properties. You want a molecule which has all green properties. It is not harming the environment. You ask AI to predict what kind of molecule we should design, and it helps with that. I'm using AI in a lot of, right now I'm writing books. I use AI to help me not to write the book because I want to use whatever experience I've gained teaching for so many years, but to help me polish it. So that kind of help, of course, everybody uses for from AI, but think about this, that you feed in data about all your molecules that you have and maybe from the literature, and then ask it to predict what kind of functional group will help in the calculation. Then we have process optimization, Bayesian optimization of synthesis conditions, reinforcement learning for process control. Bayesian is using probability. So Bayes theorem they use, and uh, reinforcement learning is how these molecular discoveries translate to the factory floor. So you want to optimize the process so that there is no waste, it is a green process, and from data that you already have, you can use it. Then predictive analytics is also similar. You can forecast what yield you will get, what quality you will get from whatever material you want to start with, so that whatever the factory wants to manufacture will be able to decide whether to manufacture that, whether to make that change. And supply chain resilience, equipment failure prediction, all that also can be done. So suppose you have a mechanism of you record when all your equipment failed. AI will be able to predict that this equipment is going to fail, so that you take action before it happens. So all that can be done using AI. So automated life cycle assessment, real-time green chemistry scoring integrated into um, workflows. Add life cycle assessment integrated with AI closes the loop. You can now score the full environmental footprint. You can find out what the environmental footprint is going to be, so that in that workflow, so that you can modify it accordingly so that it does not do that. Now, these are the pathways. I'm giving you some example. Retrosynthesis AI. I have also the names of some of the software, AI software. The company AstraZeneca, they have AI Zinth finder that they found, that it shows, I mean, they developed it, AI Zinth finder, AstraZeneca, the company that manufactures drugs, they identified the shortest, lowest energy routes automatically. They made this possible when you want to synthesize something. What is the best possible way so that it is the shortest? You know already that principle of green chemistry is that it should be the shortest route possible. So IBM made RxN, which also helps. You know what I'm talking about is, suppose you want to synthesize something, before doing the traditional method of synthesis, you can use these tools to find out which is the shortest method so that it takes the lowest energy, and so you are not harming the environment. Then machine learning, ML models trained on millions of reactions predict the yield, selectivity, and energy demand before synthesis. So all these machine learning models, you keep on feeding the data to the AI. This is what AI does. Na? You feed data and then it decides whether it is going to what you can it can predict for some unknown molecule what is going to be the yield of that process, whether it is going to be selective, whether something else is being formed instead of the desired compound, and the energy demand, how much energy it takes before you even synthesize the compound. The third thing where I specialize is that DFT computed reaction barriers validate AI proposed pathways and filter out high activation energy routes. Now, AI has told us that this is the pathway to use to synthesize this particular molecule. Now, AI is not, like it cannot fail. It can fail in the sense it may give you a high energy pathway, and which will defeat the purpose because you will not get any help that you want. You want to synthesize in a green way, and it gives you some high energy pathway which maybe takes a high temperature to synthesize or something. So here is where DFT helps. In DFT, we can find out what is the mechanism of a reaction, what is the activation barrier, and if you find that a particular reaction that AI has proposed has a very high reaction barrier, you do not, you leave it, you do some other reaction which has a better pathway. You can compare pathways for different reactions, and the one that gives you the least energy is the one that we will prefer. So, I mean, even for the same compound, there might be so many pathways that DFT can explore and tell you that this is the better pathway for this particular reaction. Then it can give you green metrics like what is the environment factor, PMI, atom economy. All these are from green chemistry that embedded directly in AI optimization objective functions. So when you use AI, you tell it, what do I want? I want this E factor. I want the atom economy. You design a pathway that fulfills all the 12 principles of green chemistry. You can tell it what all you want, what you want to prioritize. So all that you can do. And similarly, microwave and flow chemistry parameters are optimized by reinforcement learning agents in real time. So you can have, continuously monitor using spectrometers and all. You can find out what are the parameters, how they are changing. So all that can be integrated, experiment, computation, and AI. Now here is a graph which shows that with AI, how many energy savings we have obtained. The first one is solvent recovery. That is the maximum we get. We get, I think, 55%. This is the fourth slide. Um, yeah. This is before this. I think it was 55%. And the lowest one is peptide synthesis had something like 38%. So solvent recovery. See, most of the time, what is wasted is the solvent because you are not able to recover it. AI helped in saving all this, and DFT also helps in doing this. I'm looking at, um, you can ask it. For example, I said ML models what are the after you train it on millions of reaction, it can predict the yield, the selectivity, and energy demand. You can ask it questions like, suppose I run this experiment, it is always done at 120 degrees, this synthesis, but I want to do it as at 60 degrees centigrade. How much will the yield decrease? If it is not substantial, you can go ahead at 60 degrees. What does green chemistry tell us? That as far as possible, you should be synthesizing at ambient temperatures. That means at normal room temperature and 1 atmospheric pressure, because anything else puts a load on the system. So this is where AI can help predict, and the bar chart on the right tells you that we are able to, yeah, I can see it is 55% and the lowest is also around 24%. That is in peptide synthesis. Why is solvent recovery important? Because in the pharmaceutical industry, they use the maximum amount of solvents. So they are interested in reducing the amount of solvent that is being wasted, and they were able to do it using all these tools that they have developed. They took the trouble to develop these tools because it was very important. So now we are talking about carbon capture, carbon dioxide, which is causing all this global warming everywhere. You know, now it is a greenhouse gas. It can capture infrared radiation from the atmosphere and then keep it on the earth so that the earth feels hot. And this is now places which used to be cold, they are also heating up because of this carbon. So our first thing should be that how do we get rid of this carbon dioxide? So what you know that nowadays another new development is, and a Nobel Prize was awarded for this also, metal organic frameworks, where you have metal oxide and sort of structure which has metal oxides, and in between you have some organic molecules which and you get a hole, you know, pores inside where you can capture molecules. So people have been trying to do it for carbon dioxide, which MOFs, they're called MOFs, which are selective for carbon dioxide so that you can trap them. So these models, they predict the adsorption isotherms without synthesis. You see, without synthesizing that MOFs, there are how many? I think 1 lakh hypothetical MOF structures. Now you can't go on testing each one of them and see how much carbon dioxide they are able to absorb. So what we can do is we can use DFT to do for maybe not 1 lakh, but at least a few of them, and then find out what kind of structure helps in absorbing the carbon dioxide so that carbon dioxide does not escape into the atmosphere. The next is, okay, you have captured the carbon dioxide. What do you do with it? You can't keep it in that MOF forever. No? You want to use it for something useful. So now machine learning identifies catalysts that can be used for converting this carbon dioxide to useful molecules like methanol, formic acid, syngas that you use in your in kitchen. So these reaction networks, they are explored via automated DFT workflows. Yes, here is where you can use programming to make these automated DFT workflows. I'll come to that also. And reaction networks explored via automated DFT workflows. What we do is we look up all these reaction pathways, CO2 going to methanol, formic acid, syngas, anything else. Look for which catalyst will serve our purpose so that the reaction takes place at normal temperatures, not very high temperatures or very high pressures. So here, DFT, I keep on emphasizing on DFT because that is what I have worked almost my entire life on, and found that sometimes one of my colleagues tells me that we have made a sensor for something and we propose that this will be the structure of the complex that has formed. DFT tells me no, the structure is maybe bidentate or monodentate or whatever, something that they did not propose. So they have to change their experiment to fit into what DFT is predicting. It is so powerful now. You have to change. If DFT doesn't match with your experiment, you do redo your experiment, because over a period of time our computers have become faster. They are cheaper, so everybody has a laptop almost, and you can do some of these computations on the laptop. But unfortunately the softwares are very expensive, so unless the university procures them, it is difficult to do the calculations. And so you can also design electrocatalysts accelerated by active learning loops. This is what AI is good at. You feed data and it is able to find some correlation between the data and the structure and tell you what kind of structure you must form and then circulate. Uh, See, not only that, you something which is a byproduct of some reaction, AI will tell you, okay, you use it for some other production, you can use it for something else. So this kind of prediction that you have made something and something is a byproduct that you might have just thrown away, AI is able to predict, no, you can use it in some other process. So instead of having a factory for one particular item, you can have a byproduct and have a product for something else. I'm just thinking of this. Nowadays, you get chach at Mother Dairy for 10 rupees. It is a byproduct of, I think they were just throwing it away earlier. It was not available. Now you get for 10 rupees, and it is a byproduct of the butter manufacture, the whatever else they manufacture, milk manufacture. So this is something that one should always, when you are looking at how to minimize waste, this is what you should be doing at. So this is what AI in waste minimization, closing the loop. Now this is what we want to do. We want to minimize waste so that the we are able to improve our living conditions. Now 38% is solvent. So in the right, the pie chart shows you that the chemical waste, the maximum is from solvents, it is 38%. So what AI does is it ranks the greener solvent alternatives, that instead of the solvent that is being used, they use, you've heard of ionic liquids, nowadays they are also being used, but then AI will help you predict which one, and this Cosmo RS is part of DFT by which we model the effect of solvents on a reaction. So using Cosmo RS, you can find out what is going to be the solvation energy for a reaction, and then using machine learning and Cosmo RS you will use on a number of limited solvents and find out what is the solvation energy and so on, and then use machine learning to predict a solvent which is going to be less hazardous than the one that you are using right now. So then you have process analytical technology. It is, while you are doing this monitoring, you keep on monitoring the real-time spectroscopic data, like what is the UV, IR, and ML models, they detect and correct deviations. So before some waste occurs, it tells you that this reaction is going off tangent, you stop it. So that also is one application of ML and AI. So byproducts, like it says, what is the, it maps all the industrial symbiosis networks. One plant's waste becomes another's feedstock. So whatever is the waste from one plant, maybe they cannot use it, but AI tells you, you have a market there. You can sell this byproduct there, and you can then tie up with the other industry and use it there. So predictive maintenance, I've already told you that AI is able to predict, that there are some models that are able to predict before an equipment breaks down. It tells you that this equipment is going to break down, so you take action before that. I'll tell you something that happened recently. This founder of this industry, his grandson wants to go abroad, and he had to write um, um, an essay, a paper. He wanted to publish a paper before, because nowadays even in 12th class they expect you to publish papers if you want to go abroad to a good university. So he said that he wanted to write a paper about his grandfather's factory. So I helped him with that. So it was about maintenance. What AI predicted was that they should have a system, an automatic system, which is able to, this is what I'm saying, automatic preventive maintenance system, and not rely on just, writing on registers that this is when we got it serviced, and we expect that it will work for 6 months, next service is due that. Let AI predict that the service is due and do it accordingly. So solvent selection AI, pharmaceutical synthesis, Pfizer. This is, I'm giving you three case studies. One is Pfizer, which you know manufactures drugs and medicines. They 80% of their total waste they realized was coming from solvents. So that is why they use the AI approach. They used ML model trained on GSK Solvent Guide plus CS. They checked all the solvents which are available, green alternatives, and they checked that the ones which were good, which were not harmful to health, which were safe for humans, and also they scored well in the environment, they were taken up. Then dimethyl formamide and dichloromethane, they removed all of these, and instead of those, they used, of course, all this is patented, so it is secret. We don't know what they replaced by. But then they were able to reduce the load by 34%. And now in 12 of the global manufacturing sites, they are not using DMF and DCM. And that is all because of AI. We all know AI can do a lot, but then look at how much it is helping us humans. Then again, there is BASF, which is also specialty chemicals. So you know that they will be generating waste chemicals that will. So what they did was, um, for CO2 adsorption, hydrogenation to methanol. This is what I talked about, because CO2 we are is mm, global warming compound, but if we use it for some useful purpose, it will help us. So they wanted to hydrogenate it to methanol, and then they wanted to look for catalysts, which kind of surface and screening they did. They used DFT again because 8,000 adsorption energies. This is what we want. Okay, what are the adsorption energies for different compounds? And then AI used that training data to predict better ones so that they could be adopted. And what happened? They found three novel copper zinc zirconium catalysts which had 18% higher methanol yield. This is how AI is transforming how the industry is working. Experimental validation confirmed the predictions. CO2 utilization now is being done at a pilot scale. Then Unilever, you know what Unilever, in India we have Hindustan Unilever, and their problem was that their petroleum derived surfactants, you know, um, they manufacture shampoos, they manufacture surf and so on, and they're all surfactants. Now all these surfactants ultimately end up in the sea. So they wanted those surfactants which do not, which are not, poorly biodegradable, which can be biodegraded, and they are not harmful to fish, aquatic environments. So they also use the AI approach. They used generative ML. They proposed bio-based surfactants scaffolds and used QSAR. I told you, quantitative structure activity relationship models. And then they scored the biodegradability and aquatic toxicity. DFT validated interfacial behavior. Now the interfacial behavior was studied using DFT. DFT, what it does is, it is a kind of quantum mechanical, computational approach, and there are lots of software available. I think everyone has heard of Gaussian, but Gaussian is difficult to use for such substances. I use Material Studio for this kind of work. And what we do is that we look at the interaction between two molecules and then see what is whether it is getting adsorbed, whether it is physisorption or whether it is dissociative adsorption, chemisorption, and then predict how much energy is required, whether it is a feasible process or not. That can be done without the use of experiments. So using that, we can do a number of calculations and then use QSAR. I've been doing this routinely for so many years, but now with AI, it has become easier to do because AI uses its own intelligence also. So outcome is that they launched RSPO certified biosurfactant blend, 60% reduction in aquatic ecotoxicity, carbon footprint reduced 22% versus petroleum baseline. So because of their investment in this research, they were able to uh, you see how now the industries are becoming conscious about the harm to the environment. Now, why computational chemistry is industry's missing link? We are academicians, we are trained in running DFT calculations, we run a calculation, we do a calculation, we publish it, and it just goes waste because an industrialist is not looking at what we have published, and we get a paper, and I mean, this is what has been happening. But now what is happening is we are having a kind of bridge between academia, what we are, and what the industry does. Like I said, I never went to anyone that I want to join an industry because I'm happy writing my books and doing many other things that I'm doing. But when they realized that I was heading a large computational group in the university, I have experience of that. So this was a bonus that I can do this kind of thing also and help them make products that will be not only green, which will not change the environment so much, plus there are lots of products which are being imported from other countries because India doesn't make them. His vision was to make something that we can manufacture in India and we'll save lots of foreign exchange for our country. So that was his vision. But along with that, we can also make it viable for the environment. So this is what DFT and molecular simulation. There are two things. One is DFT only, that does for one molecule. Then molecular simulation sees how over a period of time the interactions change. So we have that. I mean, many of us can do DFT and molecular simulations, and then trained researchers who understand the physics behind the numbers, so we know the chemistry behind it, the physics behind it, we can do that. This is our plus point, the academia. Long horizon research capacity. Now, industry wants something very fast, but we are, I mean, in the university, there is no pressure to produce something immediately. Credibility. Now, when you publish in some journal which is, which has very good score, uh, what happens? Lots of peer reviewers will look at your paper and advise you, maybe improve what you have done. It has happened many times with me when I send paper to a high impact journal. More often than not, they will say, okay, do this also, do that also. And I've always complied. I've not sent it to another lower journal. I have tried to comply and I've learned a lot. I mean, in my 40 years, I've learned a lot from the reviewers who have told us. So that is why we are constantly learning. Now, what industry can bring us? They have the money, they have real problem statements. They can tell you, don't just do, what research we used to do is something interests us, we were doing it. They tell us, no, I want a better product for this. So we use that. They tell us what are the manufacturing constraints. They also want cost realities. In the end, industry only wants a profit. So proprietary experimental data sets to train and benchmark AI models. Now they have data sets that they do not share with others, but if they collaborate with academicians, they'll give you that, and you can use AI to model those. Then they have pilot plant and production data that no academic lab can generate. We do not have pilot plants in a lab. No, we only have small synthesis. When you go to the industry, you see whether it can be translated to a pilot plant, to manufacturing on a large scale. And with them, there is always an urgency and focus. They cannot wait years for a product to come, so they want immediate. So there is always a deadline. Uh, so what the partnership can produce is AI models validated by both first principles theory is called DFT and so on, and industrial experiment. At the DFT level or using your AI, you have worked out that this is a product that we can manufacture, which may be a better shampoo, a better whatever. And what the industry does is it tells you that it can be manufactured and whether at that scale also it works or not. See, we can only give you the background behind it, the chemistry behind it, the physics behind it. But in the end, what reality may be different. So you can test on their instruments at a larger scale. Then what will be the end product? There will be greener products with quantified environmental benefit. It is not just claimed benefit. We will be able to quantify it using their industrial data. That and this kind of curriculum, because nowadays you know that NEP 2020 is also trying to say that just don't do studies only for that. It should have some real world application. So curriculum can give you case studies. You can add not just some toy examples that we do, and a pipeline from PhD thesis to industrial deployment. So for the students, what I would say is that do not think whatever you are learning in class is just like that. You have, I believe all the students are chemistry students, but you need chemistry. To do DFT, anybody can get a software and do a calculation. But to understand the numbers, you need chemistry. So that chemistry, and what all you should have. In fact, I noted down what all you should have a knowledge of chemistry. You should have a knowledge of programming, a knowledge of quantum chemistry, a knowledge of computational chemistry. Only then you can synergize everything and do. So what used to be done till now? They used to synthesize a candidate molecule. How did they decide that this is what I want to synthesize? Just, gut feeling. Okay, I think if I change this molecule to this, it will work as a drug. Then experimentally they used to measure the properties. It is still being done, but they used to do that. Look at the UV spectra, the IR spectra, TGA, whatever instruments you have. Then evaluate the green metrics, because in the end, if you want to manufacture in the industry, so the law enforcement agents will always ask you whether it satisfies the green metrics, and then iterate. It doesn't work, so you do the second one, second molecule, again it will not do. The success rate used to be 1 in 10,000 only. So you manufactured 10,000, you synthesized 10,000 molecules, and only one of them. That is how drugs used to be discovered. 10,000 molecules used to be synthesized. Out of these, about 10 used to make it to the testing level, and one used to emerge. So now, how AI is changing it? It is defining the target first. What do we want? We do not want a compound which has high toxicity, because you are going to use, if it is a drug, it is going to be used on humans. It should be biodegradable so that it doesn't stay in the atmosphere for long. And besides that, it should also have high performance. Then we use some generative models, um, and they propose some candidate structures. You see, it is not fishing in the dark. They are picking up molecules based on the data that they have been fed, and they tell you these are these. Then it gives you the scores.
Ma'am,
Huh.
ma'am, we are running short of time, so can you please swift up the session?
Okay. So I was just telling all this. DFT will tell you about the top candidates, and then you synthesize only the ones which are good. So I don't know which one. So, uh, okay, energy load balancing and yield. I will. The challenge is, you cannot believe what AI is telling you. This is what I wanted to tell you. Chem GPT and all are there. You cannot trust because in the end, we will have to do a DFT calculation on what it has suggested, and then you can do. So for students, it is very important that you learn Python. RDKit is a chem informatics which is available in Python. DFT fundamentals. If you have all these skills, do not think that AI is going to take away your job. It is just changing the skills that you require. This is what I wanted to emphasize on. And computational green chemistry. And in that, this is a book that I have written and which has been published only this month. It has come. It has been done. And what makes it different from other Python books? I remember when I wanted to learn Python, my son is a software engineer. He gave me 3, 4 books on Python. They were not interesting for me because they were uh, examples were not from chemistry. Here, all the examples are from chemistry and ideal gas law and all this is covered. And I'm writing books on maths for chemistry, which will also be out soon. And for students, I just wanted to say, learn this. So what I'm saying is, AI is not going to replace. This is my last slide. So it is amplifying chemical intuition. You have to be good at chemistry to do that. Green chemistry plus AI is the defining interdisciplinary frontier of this decade. And DFT remains indispensable as the mechanistic anchored for AI proposed chemistry. You still have to do DFT. AI is not, you don't have to believe it always. The sustainability dividend of Chem AI 4.0 will be measured in megatons of CO2 avoided. If you are able to implement whatever we have said, then your workshop today will be a success because you would have avoided a lot of CO2. And thank you.
Thank you very much, ma'am, for your enlightening lecture. And it is truly inspiring to learn about the role of artificial intelligence in advancing sustainable chemistry. So, audience, is there any query or question you may ask? Okay, I think so. There is no question. Ma'am, there is a small query. What are the biggest challenges in integrating AI with laboratory scale and industrial synthesis?
See, again, time. I'm trying to do a calculation for last so many days, and DFT is also not very simple to do. Every system has its own challenges. I'm doing calculations. I told you what I'm looking for is innovative greases now. So when a grease is used in trains, for example, Vande Bharat. So what the tracks are made of steel. The surface is ferric oxide. It is oxidized steel. So that has iron has two kinds of it can be anti-ferromagnetic, it can be ferromagnetic, it can have anything. So to check all of these, it takes a lot of time. And with transition metals, everything is very, very complicated. The spin states, everything you have to see.
Yes. Thank you, ma'am. As a token of our sincere appreciation for your wonderful session, we are delighted to present this virtual certificate to you. Thank you for your valuable time, inspiring insight, and enriching contribution. Thank you, ma'am.
Thank you. मैं leave करूं? Hmm?
Now with this, we move to the next technical session. The lecture titled AI for Green Efficient Bioethane Synthesis Pathway. And I request Dr. Yamini Pandey to kindly introduce our next distinguished speaker and conduct the session. Over to you, Yamini.
It is my great pleasure to introduce our distinguished speaker, Professor Debrata Das, professor in the Department
Hello.
of Technology Hi, sir. Good afternoon.
Okay, okay, okay. No issue, no issue, no issue. Okay, 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 okay.
Okay. So, Professor Debrata Das is a former professor in the Department of Biotechnology at Indian Institute of Technology, Kharagpur. Professor Das earned his PhD from Indian Institute of Technology, Delhi, and completed his postdoctoral research at the University of Utah. He served as the MNRE Renewable Energy Chair Professor at IIT Kharagpur and has devoted over 3 decades to teaching, research, and innovation. He has also served as an IANAE AICTE Distinguished Visiting Professor and currently serves as the scientific advisor to Dhampur Bioorganics Limited. Dr. Das is globally recognized expert in environmental biotechnology, bioenergy, bioprocess engineering, and renewable energy technologies. He is particularly renowned for his pioneering contribution to biohydrogen and bioethane production that have significantly advanced the field of sustainable biofuels. His outstanding research achievements include more than 240 peer-reviewed publications, over 15,000 citations, an H-index of 71, and several books and book chapters. For his contribution to hydrogen research, he received the IAHE Akira Mitsuo Award and the BRSI Malviya Memorial Award. Today, we are honored to have the opportunity to learn from his vast expertise and pioneering work. Sir, I welcome you for this session, and I would like to request you that for this session, we have 45 minutes. Thank you.
Am I audible?
Yes, sir, you're audible.
Can I share my
Yes,
presentation?
sir, yes, sir, you can share it.
Is it visible?
Yes, sir, it's visible.
My PPT is visible?
Yes, sir, the PPT is visible to us.
Okay, okay. Okay, good afternoon to all of you. I am thankful to the organizer to give me an opportunity to share our research experiences in this in this one-day summit on Chem IAI 4.0 Summit 2026, Intelligent Chemistry for Industry 4.0 and Smart Manufacturing. Uh, Before I start my presentation, let me share the thought of Swami Vivekananda. And Swami Vivekananda says, "All power is within you. You can do anything and everything." That is the your your goal. That if you have something in your mind that you want to do, then you can do it, provided you have will force. Now, today, the topic I have chosen for my presentation is AI for energy efficient biohydrogen production technology. Now, this I divided into two parts. One is part one that will deal with the biohydrogen production technology because this might be unknown to some of the audience. So I want to explain that biohydrogen production technology. And part two is AI application for making the biohydrogen production as energy efficient. So the first part is biohydrogen production technology. Now, as you know, that question comes: what are biofuels? Biofuels are any fuel that is produced from organic matter and in a short period of time, maybe days, week, even month, which is considered as a biofuel. Now, why we are interested for biofuel? Because It is a sustainable energy source because it can be with us for a longer period throughout our existence. So it will be on. It cannot be exhausted. It will be remained with you, and if we can nurture this material with the organic waste material for biofuel production processes, then this process can be with us during our existence of the life. Now, if you try to understand that what are the renewable energy sources, that we have several. We have nuclear energy, tidal energy, hydro energy, geothermal, wind energy, solar energy, and bioenergy. Now, today I shall talk about bioenergy. And if you look at the world energy scenario is given here, it can be divided into two different things. One is called renewable variables and non-renewable variables, and it is depicted in the in the slide. Now, this is a very interesting. In the right-hand side, you see global energy potentiality. The world energy consumption is about 16 terawatt. 1 terawatt is about one one 10 to the power 12 watt. 10 to the power 12 watt means 1 trillion watt. Now, if you look at the solar energy that is available with us, is about 23,000 terawatt. So our world consumption is 16 terawatt. You see that a tiny fraction of the of the this no solar energy, if you can use, that will solve our energy problem. So the other cells given there: tidal energy, wave energy, geothermal, hydro, biomass, and wind. Now, if you look at this world consumption, energy consumption pattern that we have major consumption we have in the form of oil. Then we have coal, then natural gas, nuclear, hydro, and biofuel is about 10%. Now, this is a very interesting slide. If you look at the energy scenario now and then, as the time passes on, that you will be finding that energy demand keep on increasing, and particularly the two countries that we have, China and India, we are the vastly populated country, and our demand will be keep on increasing. And if you look at in the upper one, you will find the consumption pattern of the coal, gas, and oil. Now, first oil will be exhausted, then gas will be exhausted, then coal will be exhausted. Now, that current scenario is that the fossil fuel provides about 80% of the world energy supply, out of which oil provides 40% of the total global energy needs, and fuels 90%. In the out of this, 90% goes for the transport sector. Now, if you look at that, year that availability of this, the petroleum within 50 years it will be exhausted, natural gas 65 years, and coal is about 2000 years. Now, these biofuels that you can have in the different forms, both gas and liquid, it can be how it can be synthesized and recycled to the system is shown here. Now, here I want to tell the importance. It is biodegradable, stability, environmental acceptability, and the reduced dependence of the fossil fuel. Now, biofuels we have in different forms. We have biohydrogen, we have biomethane, we have microbial fuel cell. Microbial fuel cell is considered as a green fuel. The reason is that waste material will be directly converted into the electricity. Then, as per liquid fuel is concerned, we have butanol, biodiesel, and bioethanol. Now, this is the trend of fuel usage. This is very interesting. If you look at our civilization, we start with the consumption of the wood as a source of energy. Now, slowly, we change over to the animal fat, then coal, then petroleum, then propane, then natural gas. and ultimately we are switching to the hydrogen. Why hydrogen? Because it is pollution free. Because it is pollution free because hydrogen when burned it produces water, and as you know hydrogen when passed through the fuel cell we can generate the electricity. The type of organic waste that is used for the generation of hydrogen may be divided into two different types of waste. One is solid waste and the liquid waste. Now, solid waste we have different. We have municipal solid waste. We have agricultural solid waste and industrial solid waste. Liquid waste we have industrial waste and the industrial wastewater and the domestic wastewater. Now, if you look at the waste to energy technology that is with us, in the biofuel we have biohydrogen, biomethane, bioethanol, biobutanol, biodiesel, biooil by pyrolysis, and liquid fuel by the hydrothermal liquefaction. Now, gasification technology we have hydrothermal gasification, syngas by plasma pyrolysis, syngas production pyrolysis. Incineration technologies with augmentation of thermal power station and heat generation for household users. Now, this is the hydrogen economy. If you look at it, it's like this air pollution, it's safeguard the air pollution, global warming, environmental destruction, economic dependence. Now, this is how the cycle that works in the hydrogen economy. If you look at the hydrogen, the calorific value, it is 143 kilojoules per gram, near zero pollution because water is the byproduct and potential production from variety of renewable resources. Now, hydrogen can be produced in two different ways, one non-biological and biological. Now, this is the non-biological way. We, as I pointed out, the thermal and thermochemical methods. We have photo and photochemical methods. We have electrochemical methods, steam reforming and partial oxidation. And finally, we have electrolysis. As you know, the electrolysis process is largely used in our country because our honorable Prime Minister Narendra Modi ji that he want to explore this process is much a bigger way. But major problem with this electrolysis process is the life of the battery, life of the electrolyzer. The life of the electrolyzer is about 2 years. So after 2 years, approximately after that, you have to replace the electro, which is incurred lot of that non-recurring expenses. Otherwise, it is very cheap, easy to use. Now, why biohydrogen? Biohydrogen is defined as hydrogen produced biologically, most commonly by bacteria, algae, and archaea. Now, this is the biological process that we work, and we in the different forms. We have advantage of the biological process is that it operated at operated ambient temperature and pressure and atmospheric pressure, thus less energy intensive, environmental friendly. Then can utilize the renewable energy source which are inexhaustible. Now this is the reaction that just how this light dependent process biophotolysis and biofermentation, light independent we have dark fermentation and microbial electrolysis process. So I will be talking mostly on the dark fermentation process. You know the stoichiometry is like this. If you use the glucose complete oxidation, it produces 1 mole of glucose produces 6 moles of carbon dioxide and 6 moles of water. When it passes through the dark fermentation process, 1 mole of glucose produces 4 moles of hydrogen if it goes via acetic acid pathway. Now, if it goes via butyric acid pathway, it produces 2 moles of hydrogen. But if it produces ethanol fermentation pathway, it produces 2 moles of ethanol and 2 moles of carbon dioxide. Now, this hydrogen production process is usually carried out by two type of micropoda. One is called mesophilic and another is thermophilic. Mesophilic work as a close to the ambient temperature, and thermophilic work at a little bit higher temperature. Now, if you look at the classification based on the temperature, we have we have basophile, we have two types, obligate and facultative, and thermophile. Mostly thermophiles are obligatory anaerobe. Now, if you look at this organism, how it looks under the microscope, it is like a rod sepate, the gram negative, the interbacter Crocky IIT 0. This particular bacteria we isolated from a leaf of a particular tree from the local area, and we find this produces hydrogen to a great extent. Then we have Citrobacter 20, we isolated from oil-containing soil, and Bacillus coagulant we isolated from sewer sludge, and these also produce hydrogen to a great extent. Now, this is the advantage of hydrogen production that as I told you, it occurs at ambient temperature and atmospheric pressure. Various variety of substrate can be used for hydrogen production. No requirement of light energy. Rate of hydrogen production is very high. Some limitations are there, and that unless gaseous energy recovery, because total you cannot recover, theoretically only 33% substrate energy recovered can be obtained by dark fermentation, so less economic feasibility. So need the integration of dark fermentation with biomethanation process. This is how the biohydrogen stands for. The biohydrogen is a two component. One is hydrogen, another is methane. Now, what happens when wastewater or organic matter comes to this dark fermentation process? It produces hydrogen and carbon dioxide, and the metabolite that it produces mostly the organic acid. And this organic acid, when it passes through the methanogenic reactor, it produces methane and carbon dioxide. So now if hydrogen is mixed with methane, as we know that methane production process is well established throughout the world, because this has been started long before, and this is successful. This was very much successful. So now this hydrogen, if we mix with maybe at 12% of hydrogen is mixed with methane, the characteristics of the fuel increase in such a extent the operational that difficulties that can be removed, that can be removed to a great extent. Now, this is, if you look at the process, how it occurs, complex polymer, we have polysaccharide, protein, and lipids that usually degraded to the different monomers and oligomers like sugar, amino acid, long chain fatty acid, and then it is ultimate product is volatile fatty acid and ethanol. And this during this production process, we produces hydrogen and carbon dioxide. And this organic acid, if you look at, it passes through the biomethylation process, produce methane and carbon dioxide. And this is the stoichiometry we have. Then if 1 mole of glucose is totally converted to 3 moles of methane can be produced. Now in the biohydrogen production process we can produce that that 4 moles of hydrogen, and also that acetic acid also can produce 2 moles of methane. So your conversion efficiency increased by 91%. Now, this is the Tata hydrogen that fuel cell bus that is already in the market, and lot of cars, lot of 3 wheelers, lot of 2 wheelers are in operation with the hydrogen. And this is the biogas bus that is operated in the foreign country. These photographs I took from the Sweden when I was there. They're regularly running the bus with the biogas, what we call CNG. This is the advantage of the biohydrogen process from the organic material which containing the high COD beauty that can be easily converted to methane and carbon dioxide. Now this is my major publication that we have. I am glad to share with you one of my publications that we have That is the review paper. That is hydrogen production by biological process. A survey of literature. The citation number is about 2,955. Now I have my H index about 72 and 10 H index is about 171. And this is the how we develop this process. This is the book we published on biohydrogen 12 for the future, published by Pan Stanford Company. And this is the process at the bottom. This is the research paper at the bottom that we have published. This is the how we hydrogen production process we developed at IIT Kharagpur. We started with serum bottle, then we have small this fabricated reactor, 500 liter reactor, milliliter reactor, then 2 liter reactor, then we have 20 liter reactor, then 500 liter reactor, then we have 10,000 liter reactor. Has been successfully operated. Now, if you visit our website, www.bioh2iitkgp.in, you can see the live presented live demonstration of the 10,000 liter reactor. Now this is how this reactor look. In the right hand side, you can see this is how where our plants are located. This is the detailed analysis of the process, and this is the different data that we obtained. Because one thing I want to highlight that as we go for scaling up of the process, our rate of that amount of hydrogen production that has been increased to a great extent. This is the technology that has been transferred to the Rampur Sugar Mills Limited on the 3rd May 2019. Now, this is about our work on this. The part two is the AI technologies. That is why I am here to share with you how the artificial intelligence say that how make this process more energy efficient. Now, the artificial intelligence is transforming the traditional bioenergy plant into intelligent and self-optimizing and self-efficient production system. That I am going to show you how you can make it. Now, question comes: why you do why you do why we need the artificial intelligence? We need the artificial intelligence because traditional hydrogen plant face many challenges like high electricity consumption. Mainly, our electricity consumed for the starter. Because if you want to run the starter, the energy consumption is mechanical starter. It required very high power. So this is to be optimized. Unstable gas formation. As you know, the characteristics of the raw material changes, the gas production also may change. Human dependent operation, the human error might be there. Unexpected equipment failure because lot of pumps, other things, temperature control, other things are involved here. So that is to be controlled in a proper way and high operating cost. AI will help to solve this problem automatically. Now this is the how pictorially it can be that that take into action. This is in the left hand side. If you look at this is our smart biorefinery where data driven, automated, and efficient. Because this is already in practice nowadays. That we have feedstock, we have conversion, product, and monitoring. We have already there. But here we have the biohydrogen process in the right hand side. You see hydrogen and methane production. And we mix the two gases here. Biohydrogen we can sell it together as a biohydrogen. I told you this biohydrogen the characteristics, fuel characteristics of the biohydrogen much better than the methane as as a whole. Now it is now what AI can do. AI can maximize the yield, reduce the energy use, predict and prevent the failure, and real-time decision making. The real-time decision making is very important as per AI technology is concerned. Now here, what AI can do? AI work like a intelligent plant operator. It can monitor, it can learn, it can predict, it can decide, it can optimize and save energy. So this is very important because this is what we want actually. That that is we want to save energy and we optimize the whole process. Now, if we graphically presented, it will be like this. It is it is sensor, then AI brain. Sensor gives the data. AI brain works think about that. Then it takes the small decision and efficient bio Python production that takes place. Now, next is here that AI collect the data from everywhere. That is smart sensor are required. Like temperature, we have a sensor, we have pH, we have sensor, gas production, we can easily measure by using the different gas monitoring flow monitoring systems. Mixing speed we can easily monitor because mixing speed is very important for the biological system because you cannot have the very high mechanical agitation. If you have very high mechanical agitation, it gives the searing effect, which can inhibit the growth of the cell, or this can kill the cell. Then we have organic acid that production that we have in the system. Then we have power consumption. The bioreactor surrounded by biosensor that sending data to AI. Okay. Now, this is how it is done. This is the sensor that we have. This is with the bioreactor. Then it goes to the AI brain. You can see the AI brain. Then it optimizes. It makes the decision that, by optimizing temperature, optimize temperature, adjusting the mixing speed, control feed rate, regulate pH, balance hydrogen and methane production. Then we have efficient that biohydrogen production. This is the higher yield, low energy use, predictive maintenance, cost effectiveness, and environmental friendly. The machine learning, as discussed by the early that speaker, that predicts the future performance. This is the very unique system that AI has, that is machine learning, that predicts the future performance. Now, it defines as the machine learning is the process of teaching computer to learn the pattern from the data so that they can make the prediction or decision without being explicitly programmed for every possible scenario. So that is the capability they have. Now, what can AI can predict here? It can predict the hydrogen production. It can predict the methane production. It can predict the energy consumption. It can predict the process efficiency. Simple analogy is that just like a Google map for predicting traffic. As you know, when you go outside and new place, always we use the navigator just to find out where to go, how to go. The AI predicts the reactor performance. AI also has similar type of vision that if we give the data the AI properly, and the AI can help you out to find out how you can get the maximum amount of hydrogen production, how you can get the maximum amount of methane production, how you can reduce the energy consumption, and how you can increase the process efficiency. This is so AI helps us save energy by without AI we have excessive mixing, we have overheating, we have wasted of electricity. Thereby only the required energy is used. Result is low energy electricity bill, high gas production, then low carbon footprint. Visual the before and after. If you look at here, that we have a digital twin. I already found out that some speaker in the morning session he talk about the digital twin. That I hope you have some idea on that. This is the virtual copy of the real bioreactor. We have real bioreactor, we have digital twin. AI continuously compare real plant and virtual plant to improve the operation. So this is how it looks. the real plant and virtual plant to improve the operation. This is in the left hand side you have the real plant, and right hand side you have the what you call virtual plant. Is it the digital twin that we have? And this compare the performance, direction, detect the deviation, find the optimal condition, and recommend the action. So this is how it can be used. This is so AI detect problem before they work. That is the major advantage. What you can manual system takes lot of time. It can problem, repair, production loss, AI method, early warning, prevent, and failure and continuous production. As you know that in the day-to-day life when we take a lot of precautionary measure for safeguard ourselves as per health is concerned. So like this, so if you have some kind of precautionary measure that we take the action early stage, then we can prevent and failure in the production process. So that a lot of loss you can prevent. Now how we can do that? Suppose that AI can tell us in advance the pump failure, whether some activity of the pump is going to have some problem, and sensor malfunctioning, whether some sensor they are not functioning properly, gas leakage problem, particularly in the hydrogen production process. This is a major issue because hydrogen, as you know, there is a lot of safety issue involved with this. Blockage in the pipeline, that is also major issue that we have, that can be predict the AI in advance so that we can take action so that our production can be uninterrupted. Now here AI automatically optimizes the process. AI adjusts the feeding rate, temperature, mixing speed, hydraulic retention time. As you know, hydraulic retention time is about what is hydraulic retention time is the how much that liquid resides in the reactor. So this is that is counted less the hydraulic retention time, and that rate of hydrogen production will be more. Then pH. This is very important that things to be adjusted because pH plays very important in the role in the biological process. The result is that high hydrogen production, higher methane production, and less electricity. So AI and Internet of Things, what you call IoT, is the thousands of sensors. It counts to the cloud computing. Then artificial intelligence will work on that. Smart control and energy efficient biohydrogen plant that we have. Now, if you look at the benefit of AI powered biohydrogen production process, we have traditional plant, we have AI powered plant. Traditional plant manual control, then energy high energy use, frequent shutdown, low productivity, and more emission. Now here in the AI power plant, we have automatic control, lower energy use, predictive maintenance, and higher productivity and cleaner production. Now, smart biohydrogen plant part of the future plant includes the AI, cloud computing, IoT sensor, then digital twin, robotics, and mobile monitor. And as per IoT sensor, I want to just point out my student work on this microbial fuel cell for a long time, and we developed a paper-based microbial fuel cell system to monitor the temperature of a particular process. So this is IoT-based sensor we developed for that. Now this is how we can operate this whole plant with the help of this just mobile. You can have this hydrogen plant, all the information here, pH, temperature, pH, pressure, and gas flow, everything we can have. We can monitor this. This real-time monitor, smart control, AI-powered optimization, energy efficient, predictive maintenance, and sustainable future. So these are the things that we have here. And environmental benefit that we have, AI help to reduce the carbon emission, as my previous speaker talk about a lot of carbon emission. Carbon emission plays very important role, and I was talking about hydrogen, because hydrogen, when it burns, when it produces only water, no way hydrogen emission take place. So, but this is a high carbon emission. It helps to reduce the carbon emission, electricity consumption, and water usage. That is very important. As you know, water is very costly. Waste generation, waste generation also very important. More waste, more money involvement is there to safeguard our environment. The support we have net zero and circular economy and sustainable development goals. These are the these are our that target that we have. Now, future vision for this biohydrate plants is like this. We want to run it 24 into 7, because throughout the year I want to run it, learn every day that what are the problems that we have, repair itself, uses the minimum energy, and produces maximum renewable fuel. This is the future with the artificial intelligence. Because this, if we can do, then artificial intelligence really can help us to make the system very very economic, very very attractive, and so that our world will be safe. Now, key take-home message that I want to give to all of you, that biohydrogen is a very much promising for high energy recovery from organic waste, because if you go only hydrogen, your energy conversion might be 33%. If you go for combination, it is about 91%. It's quite high. AI makes the biohydrogen production smarter, because the problem you can overcome very easily, because you can, before problem occurs, that AI will tell you that's a problem, so that you can rectify the problem. You can run the process without any interruption of the process, or interruption of the operation. The AI reduces the energy consumption. This is very important. AI improves the hydrogen and methane production. AI prevents the equipment failure. AI supports clean and sustainable energy. The final message that I have, the future renewable energy is intelligent, digital, and sustainable. Again, I am repeating, our future renewable energy is intelligent, digital, and sustainable. This is this message I want to give to all the audience. Now, before I end, I want to thank, I will acknowledge Department of Biotechnology, Government of India, Ministry of Renewable, New and Renewable Energy Sources, MNRE, Defense Research and Development Organization, DRDO, then Department of Science and Technology, DST, National Science Foundation, NSF, USA, and German Academic Exchange Service, DAD, for for their for financial their contribution for our research work. Our major collaborative institute is University of Miami, Oslo University, Norway, Uppsala University, Sweden, Denmark Technical University, Ruhr University, Germany, Indian Institute of Chemical Technology, Hyderabad, TEDI, New Delhi, and Jawaharlal Nehru Technological University, Hyderabad. This is the book we published in the, that is on biohydrogen production, fundamental and technology advances, published by CRC Press. This is published 2014. Then we published this book, The Biohydrogen Fuel for the Future, published by Stanford Publication in Singapore. And this is the new book I have written. This is Biohydrogen, a simple story of green fuel, because uh, so that but understanding a cleaner future from waste to fuel, because I have written this book in the story form, so that it is acceptable for the general reader, because I request all of you, please go through that. This has not published, goes to the market yet, but as soon as market goes to the market, I shall inform you. And this is the another book we published, Fundamentals of Biofuel Production Process. We have discussed all the biofuel production processes here, and this also published by CRC Press. Then this we published recently, that is, this is the Environmental Biotechnology, Advanced Technology for Combating Pollution. This published by Springer. This recently it has come to the market. And thank you very much for your kind attention. I shall appreciate you if you ask some question. Hello.
So we have few questions to ask. The first question is, sir, that as we saw in the presentation, wastewater was taken as the source for production of waste for this biohydrogen. So is it only wastewater, or can we use our waste feed, food stock, or the agricultural waste?
Okay. Let me tell you, any kind of biodegradable material can be used. Any kind of biodegradable material. In the kitchen waste, my student has worked with all type of waste. Kitchen waste, municipal solid waste. We have that municipal sewage water. We work distillery effluent. We have starch-based wastewater, starch industrial waste. Different type of waste we have used, and we find that it can be used for the, and it is a very simple process, very simple process. If you when I can tell you a small thing here, because since all audience is there, then you know that biological process is a system where the living organisms are playing very important role. Now living organisms like human beings, because a mother and child relation, mother has the feelings for the child. Why? Because the child is with the mother from the 0 hour. Because that is the thing. Now, when we handle any kind of living system, if we work very closely with the living system, you can handle it very nicely. But if you work with a like a chemical process, you cannot handle. The living system are very sensitive. So you have to handle very with care. Like glass. If you handle in proper way, it will break. So that life and you can see your baby. If your temperature little bit you change, your baby will be uncomfortable. So that you compare with this, you can easily handle the biological system. It's very nice. Very nice, and I am happy to report here that I operated 10,000 liter reactor. It is just like a mini in the plant, actually, the industrial plant, where we have utilities one side, where at another side we have production, another side we have analytical lab. So I try to work in a manner so that student has the experience how the industry works, because I work with the industry, because I work with the sister company of Bombay Dyeing Goods. There I work with citric acid production process by using Aspergillus niger. So I have the industrial experience. So I try to share my experience with the students.
So one more question, like right
Yeah.
now E20 fuel is very much in hype. So like,
Yeah.
is it possible that we can even use this biohydrogen in future as a fuel or as a
Yes,
blended fuel?
because that I told you already, CNG is in the market. Am I right? The compressed natural gas. What is compressed natural gas? Compressed natural gas is the methane. Am I right? Compressed natural gas is the methane. Now, if you mix that 12% hydrogen with the methane, the characteristics will be improved. So more easily it can be used. You get my point. CNG is already we are using in the operating four-wheeler, three-wheeler, two-wheeler. Already we are using CNG. The CNG just with mix with 12% of hydrogen, your efficiency of the fuel that will increase to a great extent. Okay.
Okay, sir. Mr. Uday Som, you have raised your hand. So is there any query with you?
Can you hear me?
Sir, yes, sir. You can ask your question.
Yeah, thank you
Yes.
for giving me the opportunity. Sir, I want to know that I have a chemical engineer, so I working in the industry. So how can I use this biothin in my practical life in the industry? So can you tell me some scope or something about these things? So,
Yes. So may I know which industry you are working?
So I am doing on the chemical industry. Looks like the hydrogen production, hydrogen peroxide production is these types of. Yeah.
Oh, you're already involved in hydrogen production. Am I right?
Yeah. And also my research on also used the DME, dimethyl ether productions, these types of.
Okay.
So that.
Okay. Now let me give
Thank
my
you, sir.
give my input to that. Now, it is very
Thank you.
nice that nice to know that you are working with that hydrogen production process. Now, now the process that we talk about that can use any kind of organic waste. Like I can give the example of distillery effluent. We have lot of distillery industries in India. So some of the distillery industry, they have successfully implemented biogas production process, and you have seen that 50% of their fuel consumption in the distillation plant they make from this biogas. Am I right? Now, what I want to tell
Yeah.
that if you
Yeah.
now if you look at that biomethanation process, it is usually operated by two groups of micropoda. One is the acidogens and it is methanogens. Now, acidogens they produce hydrogen. Methanogens they produce methane. Now, if you have two reactors instead of one reactor, if you put the distillery effluent in one reactor and produce hydrogen, and second reactor you pass this organic acid that produced to the second reactor for methane generation. So one reactor you will produce methane, another reactor you are producing hydrogen. Then you blend it. You can blend very easily. I told you 12% hydrogen. If you blend with 88% of methane, the fuel characteristics increase like anything. So it will be much better than CNG, compressed natural gas. So you can use that. This very easily. This is in practice in the foreign country.
Mm. Thank you, sir. Thank you. Namaskar. Thank you. Namaskar.
Thank you. Namaskar.
Thank you so much, sir, for the session. It was very insightful and very interesting. Thank you so much.
Thank you. Thank you very much. Namaste. Can I leave? Should I
Yes,
leave?
sir. Yes, sir.
Oh. Thank you for your help.
So thank you for your lecture, sir. We now move to the concluding session of our summit. And the topic of this session is From Atoms to AI, Materials Chemistry for Next Generation Memory and Computing. I request Dr. Ashok Kumar to briefly introduce our next speaker, Dr. Bhagwati Prasad, for this session.
Thank you, Dr. Ashima ma'am. It is my again great pleasure to introduce Professor Bhagwati Prasad Info, young investigator and faculty in the Department of Material Engineering at Indian Institute of Science, ISC Bangalore, where he leads the Disruptive Electronics, Materials and Nanoelectronic Devices deemed group. With over 18 years of research and technology development experience across academia and industry in the India, UK, Germany, and United States, Professor Prasad has established himself as a leading researcher in electronic and magnetic materials, quantum materials, non-volatile memory, neuromorphic computing, AI, hardware, and magnetic sensing. Professor Prasad earned his PhD in material science and metallurgy from the University of Cambridge and has held research position at Tata Steel, the Max Planck Institute of Solid State Research, University of California, Berkeley, and Western Digital before joining ISC in 2021. He has published more than 50 high-impact research papers in journals such as Nature, Nature Materials, and Advanced Material, and has built an outstanding intellectual property portfolio with 65 plus patent, including 34 grant US patents. His exceptional contribution has been recognized through several prestigious honors, including the Infos Young Investigator Award. Today, Professor Prasad will deliver an invited talk on From Atoms to AI, Materials Chemistry for Next Generation Memory and Computing. We are truly honored to have Professor Bhagwati Prasad with us today. Please join us in extending a warm welcome to our distinguished speaker. We welcome you, sir.
Hey, can you hear me? Am I audible?
Yes, sir. You are audible, sir.
Okay, great. Thank you. Thank you very much for this invitation. And thank you very much for introducing me here. Okay, so I mean, my talk is a bit different than what probably this conference is all about. I'm not a chemist, by the way. By training, I'm a physicist and material scientist. So I'll be mostly talking about devices and computing technology and all those things. Okay, so okay. So let me start my talk. What I'll do is that because I have been many places, and I think most of you are student here. I hope so, and so it would be interesting for you to see what kind of ecosystem is around in the world, and then I'll tell you about those things, and then basically you can also learn from that. Okay, and then you can ask me questions. So yeah, let's go this way. Yeah. Okay, so can you see my presentation?
Yes, sir. Yes, sir.
Okay.
So can we have, yeah, it's full screen now.
So I'm talking about atom to AI, materials chemistry for next generation memory and computing. Okay. So you might see many logo here is because that I have been so many places. Okay. So I worked in industry, in Tata Steel, as well as in Western Digital in San Jose, USA, basically in Bay Area, California. And then I have been also many institutes like IIT Kanpur, and then University of Cambridge, and then UC Berkeley, and Max Planck Institute for Social Research in Germany, basically. So okay, so let me tell you what I have been doing for last several years. So I did my MTech from IIT Kanpur in material science, and there I worked on magnetic nanoparticles. So we basically synthesize the magnetic nanoparticles and figure out how we can use them for various applications. So we published a couple of papers on that, and then actually I joined industry in Tata Steel. Basically, as I told that I'm a physicist by training. So in a Tata Steel, my work was a bit different than what Tata Steel typically does. So they basically manufacture the steel, but I did very different. I developed something very novel there. I figure out how one can actually put the photovoltaics like solar cell on the top of the steel. Okay, and then we can use this for building integrated photovoltaic purpose. So basically your photovoltaic cell could be the part of the building. Okay, so for that steel is very rough, so you need to first do some chemistry or some sort of coating on the surface with some polymer coatings, and then you make them smooth, and then you put some photovoltaic cell on the top of that. In addition to this, we have done some interesting work where we basically use the steel industry waste oxide materials like a iron oxide, which is actually they generate tons of those oxides in steel industry, and we developed some water purifier with that water filter. Okay, and we have done some testing of those purifier. Okay, this water filter in the arsenic affected area of West Bengal. We did long study. It was long back. This work was done long back, but this has very big impact actually. And in fact, we developed some water purifiers, cheapest water purifier, which can actually remove pretty much 99% of the arsenic contaminations from the water, drinking water. And that solution we provide for the community. So we filed few patents and published one paper in one of the leading journal in this field. And then I went to University of Cambridge, UK, and I did my PhD on different things. So I worked on oxide materials, particularly oxide magnetic materials. and we developed a technology to actually, make some sort of devices that can be useful for data storage application. Okay, so that was fundamental work though. I mean, we discovered some new physics, basically new devices we made, where we basically figure out how one can filter the spin of the electron. So electron has a two spin up and spin down, and we develop a device, a real device means a working device, where the up spin electron or down spin electron of the electron can be filtered. And so hence you can get the highly spin polarized current. And those kind of devices are useful for memory applications. Okay. So then after my PhD, I joined Max Planck Institute for solid state research. That is in Stuttgart, Germany. So in Germany, there are 80 Max Plancks. So I joined one of them as a scientist. Okay, so this place is in Stuttgart basically, and I work very closely with the Nobel laureate von Klinsing and Johann Meinhardt's group basically, and there we develop a very new interesting stuff. So I'll be a little bit talking about this work today, which might be close to what many of you might be having the background. Okay, so we develop how one can pattern the liquid, for example, water actually, and then how we can actually integrate them with a electronic devices. So the idea was that how we can make a circuit, something like a brain basically. As you know, in our brain we have neuron and synapses, and these neurons basically get polarized and depolarized through the synapses. Okay, so ideally what happens is that some electrolytes basically containing those ions, and those are the one that moves. Okay, and that creates some sort of trigger in our brain and then creates some complex pattern. So we were trying to actually mimic similar kind of device in the real world. Okay, so then after that, I spent some time at the University of California, Berkeley. Okay, so you might know about University of California. It is in close to San Francisco. Okay, so there I worked on a completely new logic system, which is called the magnetoelectric spin orbit logic, with the Intel team. So the team from Intel was working very closely with us, and we jointly we developed a new technology. And in fact, the outcome of this work was so great that one startup company came out from that, and that startup company right now has the valuation of around $3 billion US. Okay, so they are actually developing a new memory technology for AI and for next generation AI computing. So basically, whatever AI things that you do, the hardware for that, like how AI runs in real world, for that you need a hardware, and the current hardware is not very good for that purpose, because the current hardware is not meant for doing all these kind of high-end data analysis. It was mainly meant for doing basic routine things that we have been doing. So as a result, what happens is that if you develop the AI infrastructure today, you basically need a lot of power basically, and hence it become quite expensive and power hungry. So to make it energy efficient and faster, well, one has to develop a new technology, and this is exactly what we have been doing. So we're really making the hardware for your AI systems basically. Okay. So that is what we have done. So we developed the technology on that, and we published several great papers out of that work in Nature Materials, Nature Communications, and many other journals. Okay, and then after that, I went to a industry, Western Digital. Okay, that's again in San Jose, in Bay Area, close to San Francisco. Okay, so that company, many of you have used the Western Digital hard disk. Okay, so Western Digital is basically some part of the Western Digital that used to belongs to IBM. So IBM was the company who actually did all sort of development in the memory technology since the beginning. That include your floppy drive, CD-ROM, hard disk drive, all those things. They are the one who develop all those things, who basically innovated all these technologies. So I spent time 3 years around in that place, and there we have developed a new technology, which is basically mostly based on ferroelectric and spintronics, is magnetic based technology, memory technology, which can solve some of the problem, as I told you, of the problem of the current computational architecture. Okay, so for that we need to figure out. So I'm a material scientist mostly, so we basically need to find the materials chemistry and get the right materials with the right parameters and specs that match the need for those devices. Okay, so we filed 40 plus US patent, and most of them has been granted. So for last 4 years, my group at ISC Bangalore has been working on various electronic, magnetic energy, and 2D and quantum materials. We basically make devices in spintronics, iontronics, ferroelectric, and magnetoelectrics. Then we make some interesting new hardware technologies, which is basically for AI and IoT and quantum computing. And then we also work on non-volatile memory and data storage. And we work on the various sensors as well, which include the magnetic sensors, biosensors, neurosensor, even sensors for virtual and augmented reality. So we really make the devices where this AI, all AI related, IoT related things does work. So we make the platform for those. Okay, so we start from the scratch. We work on the materials. We first synthesize the materials by various techniques. Okay, then we make some test vehicles, some test devices. We measure those devices, and then eventually we integrate those devices with the rest of the electronics, and we make some sort of technology or a new hardware technology for quantum computing, in-memory computing, and neuromorphic computing. So this is what we do basically. Okay, so this is our experimental facilities. I mean, for that you need very high-end facilities to grow those things. So we have a high-end deposition systems, PLD, sputtering, various other tools where we deposit these complex materials, multi-layers of these complex materials. We can grow ultra-thin layers as thin as even like 1 angstrom, basically few atoms we can grow, and we can precisely control the thickness and precisely control their stoichiometry, chemistry. Sometimes we grow really complex systems of 6 to 8 elements and with a very complex phases, and we basically have, find our conditions where we can really optimize the thicknesses and the quality of these films. And after growth, we basically do their detailed characterizations, and that includes structure like a TM, XRD, XPS, all those things. And then eventually we make some devices. And so then we measure those devices with the system, with the testing setup that we have, okay, for transport and magnetic and magneto transport measurement setup. And then this is, you can see the facility that it's not from my lab, but this is the kind of facility we basically use. Okay, and so yeah, and that's how we do. So this is my group. You can see that there are like around 20 students, nearly 12 to 15 PhD students, and several postdocs and masters. Okay, and we have been getting funds from various agencies. So really thanks to them, because of that only we could really manage to make our lab and running our group, basically research activities of our group. So these are my collaborators. I have been extensively collaborating with a lot of international people from all across the world. That includes in academia as well as in industry. So we are doing basic fundamental research, but at the end, our aim to develop some new technology out of that. Okay, so this is, you can see our recent research work published in various journals. So we have demonstrated how one can switch the magnet, okay, with the electric field. So typically you switch the magnet, like magnetic materials, by magnetic field, but we have discovered a new physics that how one can switch these magnet with the electric field, and then we can use them for some devices application, memory devices applications. We also demonstrated how one can use ferroelectric materials, which is basically having a ferroelectric polarizations, and we can use them for memory applications. Okay, and then we have been working on various memory technologies. So we filed several patents, and then also we have made a completely new, fundamentally new device, something called the spin filter tunnel junctions, where we can filter the spin of the electron, and hence you can use them for also for memory applications. Okay, also in collaborations, I have been working also on polar skyrmions, where we can see some exotic polar, skyrmionic phases of the dipoles, electric dipoles. Okay, we do a lot of interface cell electrostatic engineering, and we make neuromorphic computing devices as well. So this is how it works, basically material to devices and eventually for the technology. Okay, so let me now come to today's talk. So as my group also, my group name is Disruptive Electronic Materials and Nanoelectronic Devices. So we do work on disruptive technology. Okay, so what is a disruptive technology? So best example of that is your smartphone, right? So many of you are young, you haven't seen probably the old phones, and you never had that experience. But in our, when I was in a school kid, that time we were not having even the phone, the conventional phone. Okay, so when smartphone came, it basically changed the world completely. Now it can actually take care of many things. And just besides calling, it can do a lot of things. It can actually act as a camera. You can use it as a calculator. You can actually do anything you want to do that is possible with your laptops, computers. Okay, so it basically has become an indispensable machine for you, for everybody, and it's personalized as well. Okay, so that kind of technology create disruptions. Okay, so we believe on the disruptive technologies, and India really needs the disruptive technology which change the world. And those things actually initially take some time, but eventually they will cross all the barriers and will become quite popular in the masses. Okay, so if you look current, where we have a potential for disruptive technologies. So if you see that this is the McKinsey company has done some survey, and they found that there are 12 disruptive technologies that can make a big impact in the whole world. Okay, and those technology has a potential of approximately $100 trillion. So that means we have a huge opportunity to do something great and get some big businesses out of that, and some new innovations in that area. So if you look at many of them, like a mobile internet, automation of knowledge, internet of things, cloud, advanced robotics, many of those, if you look the top ones, they are the one which actually comprises most of the share, right? And hence you can see that those are the one which actually need some sort of data transfer from one device to device. So eventually, if you look that, you need to develop infrastructure for making all these things to happen. If you're talking mobile internet, you need some sort of hardware for that, where mobile internet work. Okay, or if you talk about internet of things, you also need some sort of sensors and technology where that work. Okay, so if you look on the other hand, the IoT, Internet of Things, basically, so this is so which you probably have heard about Internet of Things. So the idea behind that is that you basically would be having a smart life where various sensors, they all connected, and they all basically synchronized, and they can talk to each other. Okay, so that you can see that to making those lives like digitally smart life with using all those things that I told you before, that actually require a lot of data transfers and shuffling of the data between one device to the device. Okay, so to do that, you need a infrastructure for that. And for that, semiconductor industry is the one which is actually developing all sort of electronic technology. So yeah, so if you look that here, the semiconductor industry market, how it is actually has been evolved over the years. Okay, and recently, the big boom has come into this area is because of the AI and IoT. So all these companies are now making infrastructure and technologies for this AI and IoT. Okay, and that actually, I mean, it was the prediction that by 2030 this market will go to 1 trillion, but actually this prediction seems to be wrong. Even this 1 trillion market is reaching in next 1 year, basically. So maybe by 2030 this market will reach to $5 trillion the way it is going right now. So really there's a big demand for AI infrastructure. Okay, so let me now coming back to that, how that works. All those things, you have to come down all the way to the device level. Okay, so now if you look how that work, if you open your phone, mobile phone, if you look inside that, open that, you will see this kind of this chip. So basically, what is this? This is nothing but the IC, integrated circuit. What is IC? IC is actually comprising billions of transistors and other electronic devices. Okay, and they all are connected to each other one way or other. So that how you do that? For that, you need a complex processes which include a lot of chemistry, a lot of material science and electronics all together. Okay, and if you look the individual device, which is basically transistors. So basically, a transistor is the one that actually used as a logic device, which can give
Sir, your voice is not audible, sir.
now.
Now you are audible. Yes.
Okay. Yeah. So when this problem has started? Just now or hello?
You are
Can you hear
audible.
me now?
Continue. Yes, sir. Yes, sir.
Okay,
Continue,
great.
please.
Okay. Okay, so this is the basic device I mean I'm talking about, but in reality, when you make that, actually this is quite complex and very high tech kind of work. So if you look the semiconductor chip, how that get that manufacture, actually you probably know about the wafer, silicon wafer, am I right? A silicon wafer could be 6 inch, it could be 8 inch, and even 12 inch. So 12 inch is the is the current, instead of the art technology where people use a 12-inch wafer, 300 millimeter size wafer. So in that wafer, basically one is a silicon wafer. On the top of that, you can put a lot of these transistors, capacitors, interconnects, and all those things. Okay, and that's how it look like basically. So there are billions of transistors you can put in one of this small area. Okay, and eventually then you cut them and then you use them as a IC. So if you look one of these chip, okay, and one of that, how they basically connect. So here you have a device at the bottom, and then you have all these interconnects. Okay, so these interconnects could be as long as 60 miles if you basically making a chip on 10 mm by 10 mm area. So you can understand that how 60 miles is like how much, like around 90 kilometers long wires are there only within 10 mm by 10 mm logic area. Okay, and so that would be comprises more than 10 billion connections. Okay, and would be having more than 10 billion transistors, and for that you may need a lot of different kind of materials, like more than 25 different materials and hundreds of their combinations. Okay, so eventually you need to figure out the materials chemistry for that. So if you look a semiconductor industry, they hire a lot of chemists and material scientists, okay, for that. Many of them, I would say like 20 to 30% of the people in semiconductor industry are from the chemistry and material science background, because eventually for developing all those things, you need people who understand the chemistry of the materials and how they can put together, how you integrate them. Okay, so this is how the chip manufacturing happens. You basically start from silicon wafer, then you cut them, make the so you start from the ingot basically first, right? You cut this ingot into the wafer form, then you pattern those wafers, then you make some sort of transistor on the top of that by lithography, and then you cut them a small chip, and that chip you package, and eventually that then it comes to your mobile phone. Okay, so you basically from send to mobile phone, that's how it works. Okay, so it's a long journey basically. In multiple steps, you require people who understand the chemistry and materials for doing all those things. Okay, so in as I shown you my the facility in my lab, that's quite small compared to what actually you do in the industry. So industry tools are quite big, where you basically run the 12-inch vapors, and those vapors can go from one chamber to the chamber without breaking the vacuum. You deposit these materials, and then after that you pattern them. Okay, so if you look that when you talk about semiconductor, which is basically the current trend, and many of you might know that there's a lot of jobs and opportunities are there in semiconductor industry right now. They are hiring people of all backgrounds, like Micron is hiring, AMAT is hiring, Global Foundry, Tata Electronics, many of them. So what they basically, if you look the semiconductor whole ecosystem, it actually required people who understand the electronics, who understand the packaging, who understand the materials, photonics, and all sort of things. So eventually that is the one, it's like big supply chain things. It's like it's a big industry itself. It's not just one company. There are maybe more than 500 companies are involved into this whole things. Okay, so if you look, how you store the data in your compute in your like a hard disk. Basically, this is something called the hard disk drive, where you store your data permanently. Okay, so I don't know how many of you really have seen the hard disk drive in this era. We used to, like 20 years back, we used to use this hard disk drive even inside the laptop. Okay, so this hard disk drive basically they are having a disk. Okay, and on this disk we have some sort of small magnetic particles, grains basically. Those magnetic particles having a size of like 8 to 10 nanometers. Okay, and then you can actually switch them magnetically from one way to other, and then you put a head on the top of that which can read the information on that. Okay, so that's how you store the informations. So eventually you need to make sure that when you make these kind of devices, you cannot have any contamination inside. In fact, you can see that if you put a fingerprint, it can be of size of few nanometers, and that can create trouble when you are running the head on the top of the vehicle. Okay, so this is how traditionally, data are being stored like 15 years back. But now we all use a SSD, am I right? This NAND, basically 3D NAND. Okay, so earlier, like 10 years back, this SSD having a very small capacity, like 250 MB or something like that. But now we can get 1 TB, 2 TB easily. Okay, and with the such a small area, that could possible because over the years people have learned how to make the multi-story data storage capacity like that, like similar to like apartment. So when the population of the city increases, what you do, rather than making independent houses, you make the apartments, and those apartments would be having a multiple floors, and it can accommodate many people. The same way, that is how the industry is working right now. They are doing 3D integrations where they can make a multiple floor of these devices, and then hence you can actually store a lot of data into a small footprint, a small area. Okay, so all that is actually, now you can see that is actually kind of eventually required for artificial intelligence, which is bringing the disruption in the ecosystem in all sort of area, including transportation, manufacturing, healthcare, education, media, and customer services. Okay, and for that, one of the example that you can see, that one of the IoT examples, so AI and then there is IoT. This is the example of the IoT where we can talk about a smart kitchen, right? So in that kitchen, if you look, you basically everything can be controlled by your mobile phone, and you can actually transfer the data from one device to the device, and eventually this kind of smart kitchen can cook the food for you automatically. You don't need to go inside the kitchen. There will be a robot inside that will actually move the machine and things from one place to the place, and everything will be controlled from your like mobile phone remotely, and you can cook the food of your own interest. So if your family having 5 different people having different interested, if they want to eat different things, then this smart kitchen can cook those things for you. How that is possible? Eventually, you need a sensors to make this to happen, like because you want to check how much amount of salt you want to put, how much oil you want to put. That someone need to be some sort of device need to measure that, and for that you again need sensors, and the sensors actually they all talk to each other, and that is how the IoT works. Okay, so all these things require to data actually transfer, as I told you. Okay, so to transfer the data, if you look at today, we are creating a lot of data, actually 2 trillion gigabyte data. Okay, and eventually this is going to increase significantly over the years, is because many IoT devices are going to increase in next 8 to 10 years. Okay, so in the semiconductor industry, you will see that the next decade could be the decade of memory rather than the processor, memory and storage. So we don't need to worry about logic now. We need to worry about memory basically, because eventually you need a memory to transfer the data. Okay, so that's why the whole world is now looking for data centric. You probably have heard about data centers. Many companies are opening their data centers because the world has become to data centric. Okay, and at the same time, you probably have heard that it will cost a lot of power actually. So we need to think about how to make them energy efficient, how to reduce the power consumption. And at the same time, there is some problem called the memory gap issue, where your processor runs much faster, but your memory is slow. So that is another problem that need to be addressed. Okay, so for that, people have been developing some new technology, which is called the universal RAM. Okay, so let me go a little bit deeper into that. If you look at computational architecture, which is called the von Neumann architecture, and that can be represented by this pyramid. So on the top of this pyramid, you have a processor, and at the bottom you have cloud storage, and there is a flash, which is basically your local storage. And the gray ones are non-volatile, means when you turn off the power, you can keep the information there. The blue one is like a DRAM and SRAM. They are memory, but they are actually volatile. And so when you turn off the power, you lose the information. Okay, so you can store data permanently only in the cloud, in the NAND. Okay, now if you see that, if you want to take the data from there, you need a 1 millisecond to sub-millisecond time frame. However, the processor is running very fast, 1 microsecond. And because of that, you are actually, your processor is waiting for data to come. And hence that creates a wall for the computation, which is called the memory wall. Okay, and that is actually creating more trouble for AI and IoT. So that's the thing that we need to solve. The other problem is that you are storing the data all the time, okay, in a big storage centers. How we can actually, because you always want to store the data, whatever data we create, we want to store that. So how we can also make a cheap data storage solutions. So across the globe, people have been looking various ways of doing this. Okay, so they basically finding a new material systems, new sort of devices like based on spintronics, magnetic materials, ferroelectric materials, resistive ray materials, and then developing some alternative solutions for the current von Neumann architectures, devices. Okay, and so this is what we do in our group. We basically explore all these new materials and try to make a new technology which can solve those problems, the problems of the memory wall, make energy efficient, fast, all those things. Okay, so this is what we do. We develop the AI hardware. There are many companies which is actually developing all those new technologies. And in fact, we are having some collaborations with the Micron and with Western Digital and with Lam Research, and we are developing those technologies with them. Okay, so many companies are working in this area. Okay, so eventually what we are now looking for, we are looking for how we can go, in the computation side, how we can, or computations in total, basically, which includes your logic plus your memory part. If you put them together, we are looking for performance, like higher efficiency and higher energy efficiency. And that for that, we are actually right now, we are going for von Neumann architecture to near memory computing, to eventually to the in-memory computing. That is what people are now working on, and to the finally the neuromorphic computing. So that is the where we have to work to give the real support for the AI hardware. If you don't do that, the AI hardware will not work. It's not sustainable at all in the future. A lot of money is being spent by many companies, many governments, institutions, but eventually they are not sustainable if we don't solve the problems. And that's why we are getting a lot of projects nowadays to really make that happen. And it's not a problem in India; it's a global problem that need to be addressed immediately. Okay. So other way of doing these things is that completely make a new system, don't work on the CMOS. Okay, make a new computing architecture and look for a new way of computing, which is like something how our brain works. So brain required very small power, like some milliwatt power. However, many of these computing devices require a lot of powers. So can we not think of developing circuits and technology which works like a brain? That's what many companies are doing, like Intel is doing, IBM is doing. They're developing their own, this brain-inspired computing chip, which is also they say AI chip. But that's the concept behind these devices is different. They are not they basically not meant to be like a CMOS. Okay. So we also have been doing this. We basically are trying to develop those things. So let me now practically show this work. So we develop how one can actually do this with the ionic liquids. We pattern the water, ionic liquids, okay, and we basically try to make devices with that. So when you do this kind of crazy things, you see a lot of failures. So this is one of the photo that we have taken. It is actually showing that what are the issues can happen. So eventually we are able to make these devices where we could really make a capacitors with ionic liquids, which is basically a salt solution, where we integrate them with other devices, and then we can make some sort of electric double capacitors, where we can apply the voltage and we can basically create the large, capacitance, and then you use this as a passive capacitors or active capacitor in the circuits. Okay. Also, we made a transistors where we can actually use them as a gate dielectric. Okay, there's electrolytes, basically this ionic liquid, and hence you can actually connect them all these together, and you can make some interesting devices with that. That could be useful for neuromorphic computing as well. Okay. So this is how it works. So we have shown that how transistor can work. So we actually integrated this ionic liquid, and then we apply the gate voltage, and we can switch the transistor from on state to off state. Okay. So in addition to that, as I told that, we also working on various sensors. Those sensors are useful for augmented reality, virtual reality, many other things. And eventually this is what we are doing. All it would be required for AI hardware, because whenever you're talking about AI, IoT, you need a sensors, and you need a sensors to be working together. And this is what we have been doing. So we are developing magnetic sensors, which can sense as small as a femtotesla magnetic field. So you might know the Earth magnetic field is a microtesla. So we are measuring a femto Tesla, which is basically the signal that you get from your brain. So with those devices, we can actually measure the brain activity. We're also developing piezoelectric sensors for various applications. We're also developing some phase shifters, microwave filters, then also some supercapacitors, ceramic-based supercapacitors, and other functional devices. And as I told that also we are working on the cross-bar array memory. So we have been doing a lot of these things. Okay, and eventually that's the whole idea behind that, to develop the new disruptive hardware solutions for AI technology, where you need to first work on the computational side, where you need to solve this one human architecture problem. And on the other side, for IoT devices, you need to develop sensors, and you need to learn how to connect all these sensors together and do the fast data transfer between these devices. So this all required materials chemistry, materials characterizations, and this is what we have been doing in our lab. Okay, so with that, I would like to summarize my talk. So what I have told that the world is undergoing a transformative technological shift that is driven by the rapid advancement in AI and IoT. And so we need to address the limitation of the current computational devices and architecture, because they are not meant for AI and IoT. And hence, we need to really figure out on new materials, new chemistry, new device physics, and then figure out how we can put them all together and develop the next generation computing technology, which is beyond CMOS, beyond complementary metal oxide semiconductor. And eventually that is the one which will provide the new architecture and will provide the some new technology in the in this field. Okay, so with that, thank you very much for your kind attention, and I'm very happy to take the questions. My talk, I kept my talk very generic and overview kind of things. I mean, I did not present much of my work in that detail. I just shown you in a very brief way. If you're interested, I'm happy to tell more about that. But also, if you want to know more about other things, I would be happy to take the questions based on that as well. Thank you.
Thank you, sir, for your outstanding lecture and for sharing your valuable insight with all of us. Audience, do you have any query or any question? You may ask. Okay, I think so. There is no query. Sir, actually, sir, I am having a small, question to you that possibly which material will be, power next generation for AI computing, according to you, because you have done a lot of research I have seen in your lecture. So please.
Which material means?
I mean, which material will be power next generation in AI computing?
So there is not a single material. It's like a lot of materials, as I told you. Okay, so we need to figure out a lot of new materials, which is something called a functional material. So far, we have been using semiconductor materials. Semiconductor materials just give you current on and current off state. Okay, but many of the things in our life is not like that always. They are much more sophisticated than on and off, right? So for that, we need to develop this materials which is highly sensitive for many things. They are called the functional materials. For example, if you basically having a touch screen, so have you ever thought that how touch screen works basically? Okay, when you go to some of these these nowadays in these sports complexes, okay, in very big shopping malls, there you can see a lot of toys and a lot of things that kids play with that, which is more of the augmented reality and virtual reality based. Okay, and how that works, that actually all works on sensors, and how these sensors actually they can actually pick very small movement from your hand, from your brain, like how you're moving your head and all those things. They can actually pick such a small movement. And how that is possible is because these sensors are meant for that purpose. They may be piezoelectric sensor, they may be pyroelectric sensors, they may be some photonic sensors, all those things, and eventually that boil down to the materials with the functional properties. Okay, so I would say that the functional materials would be the game changer, not only having the big business game changer for the next generation computing technology.
Okay, thank you, sir.
वैसे उधर ही आ जाएंगे.
Okay, as a token of our appreciation for your insightful and engaging session, we would like to present this virtual certificate to you, sir. Thank you for your sharing valuable knowledge and expertise with us.
Okay, thank you very much.
Now, Dr. Ashma ma'am, please proceed the session.
Okay. After the So now with this completion of the technical sessions, we now move to the valedictory session of the summit. And I sincerely thank our eminent speakers, distinguished guests, faculty members, participants, as well as the organizing team for making today's summit a grand success. To present the summary of today's event, I respectfully invite Dr. Roli Verma.
Thank you, Ashma. Good afternoon to one and all present here. As we come to the close of Chem AI 4.0 Summit 2026, it is my privilege to present a brief summary of today's enriching deliberations. Today's summit highlighted how artificial intelligence is transforming the field of chemistry, from accelerating material discovery and advancing nanotechnology to enabling digital twins, smart factories, green chemical processes, bioenergy optimization, next generation materials for computing, etc. Our eminent speakers demonstrated that the integration of AI with chemical sciences is no longer a vision for the future, but a reality, shaping research, innovation, and industrial practice. The discussions emphasize the importance of interdisciplinary collaboration between academia, industry, and research institutions to develop sustainable, efficient, and intelligent solutions for global challenges. The insightful interactions and thought provoking sessions have opened new avenues for research, innovation, and partnerships. I hope the knowledge gained today inspires all of us to continue exploring the exciting possibilities at the intersection of chemistry, artificial intelligence, and Industry 4.0. Thank you once again for your participation. I wish you all continued success in your academic, research, and professional endeavors. Thank you so much.
Thank you, Dr. Roli, for the brief, crisp summary of the event. Now I invite Mr. Mahadeva Swami to present the vote of thanks.
Yes, sir. Good evening, everyone. At the outset, I humbly seek the divine blessing of His Holiness, Jagat Guru Shri Shivaratri Deshikendra Swamiji, whose visionary leadership and unwavering commitment to education, research, and service to continue the inspire and guide us all. I extend my heartfelt gratitude to our Honorable Vice Chancellor, Dr. H.R. Madhavaswamy, sir, in his absence. We are gratefully acknowledge his visionary leadership, constant encouragement, and continued support for academic excellence and research. I also express my sincere gratitude to our acting Vice Chancellor, Principal Dr. B. Manoj Kumar sir, for his constant guidance, encouragement, and unwavering support in making this international summit a grand success. My heartfelt appreciation goes to our summit chair, Professor Dr. Jagadish R.S. sir, for his inspiring leadership and invaluable guidance. I also extended my sincere thanks to our convener, Dr. Roli Verma ma'am, and coordinator, Dr. Rashima Srivastava ma'am, for their meticulous planning,
डॉक्टर
dedication.
अशोक अपना वो करो माइक ऑफ
My heartfelt appreciation goes to our summit chair, Ashok sir. To our summit chair, Professor Dr. Jagadish R.S. for his inspiring leadership and invaluable guidance. I also extended my sincere thanks to our convener, Dr. Roli Verma ma'am, and coordinator, Dr. Ashima Srivastava ma'am, for their meticulous planning, dedication, and tireless efforts in organizing this summit so successfully. I would also like to express our deepest gratitude to our speakers, Professor Dr. Murali M. Lappu, and Dr. Bonesh Sharma, Professor Vishal Singh, Professor Rita Kakkar, and Professor Debrata Das, and Professor Bhagwati Prasad sir, for sharing their valuable knowledge and inspiring insights on artificial intelligence, smart manufacturing, green chemistry, biomaterials, digital twins, and biotechnology, and next generation materials. I would also like to extend my sincere appreciation to Dr. Kirti Srivastava Madam, Dr. Ashok sir, Dr. Yamini Pandey for their valuable support and dedicated efforts in ensuring the successful conduct of this summit. I also extended my sincere thanks to all the faculty members, researchers, students, industry professionals, and participants who joined us from across India and abroad. Your enthusiastic participation and active interaction have greatly contributed to success of this summit. Finally, I extend my heartfelt thanks to everyone for your valuable presence and support in making Chem AI 4.0 Summit 2026 a memorable and successful event. Thank you all. Have a wonderful evening. Thank you, everyone.
Thank you, Mahesh. Now, before we formally conclude today's program, we have a couple of important announcements for all the participants. The feedback form has been shared in the chat box, and we kindly request each one of you to take few moments to fill the complete feedback form. Your valuable feedback is going to help us in improving our next academic programs. Further, e-certificate of participations will be emailed to all the participants who have attended the summit and filled the feedback form. The certificates will be sent to your registered email IDs within a couple of days. Now I would like to thank each one of you for the enthusiastic participation and cooperation during the entire 1 day of this summit. Before ending the session and the summit, I would like to express my sincere appreciation to the entire organizing team of Department of Chemistry for making this event a great success. Have a wonderful evening to all of you, and Jai Hind. Bhavna लिख रही है, thank you to the whole team. Congratulations. Next time we are ready to join. Join. Some recording off कर देते. Stop no.
Stop recording.
ठीक है. बंद कर दे.